Okay, I think I should make a start. So welcome everybody to this ARCHER2 course on Advanced OpenMP. I'm got a little bit of introductory material to get through. I'm going to skip over most of it in fairly quickly so that we can get on to the main topic of today. Please do feel free to ask questions at any point. The easiest way to do that is to type in the chat on the Collaborate page. So if you look down at the bottom right-hand side, you'll see a speech bubble, which gives you access to the chat window. If you click on that, you can type questions in there, and I'll keep an eye on that as we go along. Okay, right, legal stuff. Basically, the material for this course is all freely available, and you can reuse it however you like, provided you give us the appropriate credit. Okay. So I guess most of you will be familiar with ARCHER2. It's the UK's national supercomputer service. It's managed by UKRI, primarily EPSRC. It's housed, supported, operated and supported by ourselves, EPCC at the University of Edinburgh, and hardware is supplied by, well, Cray, HPE Cray. Okay, just a few details about the system. So in case you're not familiar with it, it has a little short of 6,000 nodes. So each node has 128 cores, split between two 64-core AMD Rome chips. So that gives us about just under 750,000 cores in the system. So obviously today we're talking about OpenMP. We're really focusing on what goes on inside a single node. Yeah, there's 256 gig per node, except for a few large memory nodes, and yeah, there's fast interconnect and high performance file systems. Okay, just some useful links for you. So the training page, the top link here, is where you can find the link to this course and the course materials. I've posted a direct link to the materials in the chat window for you. After this course is finished, everything will get migrated to the material from past courses. So the materials will be available along with the video recordings of these sessions. So they'll move into the past materials and they will be archived there for semi forever. Okay, until the ARCHER2 website finally dies in goodness knows how long time. Okay, let me introduce myself very briefly. My name is Mark Bull. I'm a senior research fellow at EPCC. I spend a fair amount of my time teaching on our master's course in high performance computing, as well as doing research projects. And I'm also the representative for EPCC on the OpenMP Architecture Review Board, which is the body that administers the OpenMP standard. Okay, other things, I'll remind you at the end of the course to please fill in a feedback form, but that's obviously not for now. If you have any inquiries about your accounts or access to the system, if something's not working, please email the help desk. Okay, so for purposes of this course, you all have been given an account in in TA189, which has a small amount of budget in it. Because we're running this course online, we're actually not using reservations. So I suggest that you, if you want to run the practical experiments in your own time, I suggest using the short queue for quick turnaround, because they're all just single node jobs. Okay, the accounts will be closed approximately 2 weeks after the end of the course. Everything will get wiped. So if you want, please remember to, if you want to take copies of any files, any code that you've developed, for example, during the course, please take a copy off before the accounts get blown away. Okay, we have a code of conduct. So basically it says that we expect both ourselves and everybody attending the course to essentially just behave themselves and be nice to each other. Okay, so timetable for this course. I have made a small change to this from what was advertised. So the session about the memory model will not be today, because I've realized I've now got too much material to get through today. So that's been moved until the last session on Thursday the 27th. So my sincere apologies to anybody who came along specially today wanting to learn about the OpenMP memory model. I'm afraid that's not going to happen today, but it'll happen next week instead. Okay, yeah, let you know it's giving you a direct link. For the practical exercises, there's the notes and the code is actually on the GitHub repo, but there's also a copy in a shared folder on ARCHER2, so you can just you could just copy that directly and unpack it if you want to access the exercise materials. Okay, so I hope you enjoy the course. I say please do ask questions via the chat mechanism, and also please feel free to email me outside of the course, the actual course hours for this week and next week, if you've got any questions about the practical exercises or anything like that. Okay. Does anybody have any questions before we begin? Okay, so I have a question for you, if that's okay. Because OpenMP supports Fortran, C, and C++, it would be useful for me to know so that I can give the right emphasis to the different base languages as we go along. It'd be useful to know from you whether you are most familiar with Fortran or C or C++. Okay, so one C++, C programmer, C++. Anything, Christopher? Okay, one Fortran, mostly C. Okay, that's great. Thank you very much. So we're primarily C++ audience. So there are a mixture of examples in C and Fortran. So I will, if Chen will forgive me, I will probably skip over the Fortran examples fairly briefly. So they are there in the slides for Fortran programmers. Okay. So the first topic we're going to look at today is tasks in OpenMP. Ah, yes. Thanks, Krista. Thanks, Christopher. Yeah, I have to go to the right branch. Okay, so what are OpenMP tasks? Okay, so the way OpenMP thinks about this is that tasks are just independent units of work, so pieces of computation that can be executed independently. And they're really composed of two things. So they consist of a block of code to execute and also some data to compute with. So this extends the notion that you're probably already familiar with of private data in OpenMP. So if you haven't programmed with tasks, but you've programmed with regular parallel regions and parallel loops in OpenMP, you'll be familiar with the concept of threads having private copies. And those private copies are copies of variables, and they are per thread. Okay? But tasks extends that idea a bit, so we can actually have private copies per task rather than per thread. Okay. So what we really write in the code is the code to generate the tasks. And these tasks will then be assigned to some threads in the parallel region for execution. And we essentially have no control as a programmer, or pretty much no control over how that's done. Okay, so we are specifying what are the independent pieces of computation that should be done, and it's pretty much entirely up to the OpenMP runtime to decide what order they're going to get executed in and which thread is going to execute them. So the task construct, like most OpenMP constructs, includes a structured block of code. So the structured bit just has the usual meaning. It means that the control flow has to go in at the top and out of the bottom. You can't jump in or out of the block. So say tasks. Again, like OpenMP work sharing constructs, task constructs do not themselves create threads. Okay, they only make sense if we're already inside an existing parallel region, so there are already multiple threads executing. When we're inside a parallel region, a thread that encounters one of these task constructs will package up the code block and any associated private data with it for execution. And then all we really know is that some thread in the parallel region will execute the task at some point in the future. But that actually could be the encountering thread, and when in the future could actually be right now. Okay, so we again, this is all under the control of the runtime, and we can't do very much to influence that. In OpenMP, tasks can be nested. So we can have task constructs inside task constructs. So a task may itself generate tasks and so on recursively. So we can go down, potentially write code that goes down quite a deep tree of task generation. We'll see an example of that later on. Okay, so the syntax is pretty much what you'd expect. Fortran !OMP task, structured block of code, and then end task, and C and C++ hash pragma OMP task with structured block. Okay, so just a reminder about OpenMP syntax. For C and C++, the structured block is either multiple statements inside curly braces, or it can be just simply a single statement on its own without the curly braces. So that's legal, but I generally recommend that you don't do that. Okay, I think it's good programming style, even if the structured block only contains one statement, to always include the curly braces so that it's very clear where the task ends. So similarly to other, that's the same as other constructs in OpenMP, like parallel regions. Okay, so here's first a simple example. So suppose I have something very simple. Suppose I have these 4 function calls: Fred, Daisy, Billy, and Molly, that I want to execute, and they're all independent of each other. So I don't mind what order they get executed in, and I assume that it's safe to execute them on different threads at the same time. So the usual pattern would be to include each of these in a task construct. Okay. So I need to be inside a parallel region in order for this to make sense. So because the parallel region is the only thing that really actually creates threads in OpenMP. And the common pattern, or a common pattern for tasks, is to have one thread only generate the tasks. Okay. So in this case, I've used a master construct so that it's thread 0 specifically that is going to generate all the tasks and make them available for other threads in the parallel region to execute. Using single is also absolutely fine. Okay, so you'll quite often see that pattern as well. You'll see either parallel master or parallel single as a common pattern for using tasks. So that means that that thread 0 is going to encounter all these task constructs. It's going to package up those tasks for execution, and the other threads that might exist in the parallel region are available to execute them in some order. So as I said, we don't know which thread, and we have very little influence over which thread executes which task. Okay, and the same idea in Fortran. Okay, so if we just generate tasks, how do we know when those tasks have finished? So there are several ways of waiting or checking for task completion. So in particular, tasks are complete at all thread barriers. Okay, so wherever there is a barrier inside a parallel region or at the end of the parallel region, then when the threads encounter a barrier, the barrier will not complete until all previously generated tasks up to that point have finished executing. So a barrier guarantees that all outstanding tasks complete at that point. We can also have a bit more fine-grained control. So this is the task wait directive. And what this does is that it waits until all the tasks defined inside the current task have completed. Okay. So a couple of things to note about this. So this is one of these standalone. This is like a barrier. It's like a barrier directive. It's one of these standalone directives that doesn't have any code associated with them. And it applies. It's what's called a shallow wait. So in the case where we have nested tasks, it applies only to tasks generated in the current task and not to any subsequent descendants. So it only waits for the immediate children tasks of the current task. Okay. Now, the way that's defined, it all sounds like that doesn't make sense unless we have nested tasks, but actually it does, because the code, the way standard's written, the code executed by a thread in a parallel region is considered a task for these purposes, okay, for when we're thinking about task wait and task completion. So the specification calls that an implicit task. So the whole block of code that a thread executes inside a parallel region is considered a task. So if we have a task wait, then the encountering thread will wait for all the tasks that it's generated up to that point. Another mechanism as well, and this is called task group. Okay, so this is different from task wait because it does have a structured block of code associated with it. And what this does is that the end of the task group causes the encountering thread to wait until all the tasks created within that structured block have completed. And unlike task wait, this is a deep wait. This applies to all descendants tasks and not just to the immediate children. So here's a very simple example of task wait. So suppose I have the same pattern again, parallel region, a master construct, which is going to generate the tasks. So what happens here is that the master thread will generate the task for Fred, it will generate the task for Daisy, and then it encounters a task wait. So at that point, the master thread will stop and it will wait for these two tasks to have been completed. So they're probably going to be executed by some other thread in the parallel region, but not necessarily. The master thread could also be involved in executing those tasks as well. Okay. And then once Fred and Daisy tasks have completed, then the master thread can carry on executing and generate the task for Billy. Okay. So this is a mechanism. It's can be used as a mechanism for enforcing some ordering between tasks. So this one in particular, okay, so if we have some dependency, so say Billy depends on results computed by Fred and Daisy, then this will synchronize the tasks correctly and have to get them executed in the appropriate order. Okay, it's something of a crude mechanism for that. We'll talk a bit later about how we can have more control and more finer grained control over dependencies between tasks. Okay, and the same for Fortran. Okay, so what things are tasks are good for? Where are tasks useful? And so one of the use cases, one of the common use cases for tasks is for loops that cannot be handled with OpenMP work sharing constructs. So that's really loops where the iteration count cannot be computed before the loop starts executing. So general while loops are like that. So if we have a while loop where we want to execute the iterations in parallel, we can't use a regular OpenMP do or for directive on that because those directives, those work sharing directives, are restricted to the case where the number of loop iterations is computable before the execution of the loop starts. So here's an example of such a loop. Okay, so this would be a classic linked list traversal. So linked list is one of these data structures where we have multiple items and each item contains a pointer or a index or something or some way of accessing the next item in the list. Okay, so for example, we might say, okay, we've got a pointer P. We initialize it to point to the head of the list, the first item in the list, and then we iterate over the list. So we say while P is valid, while P is not null, then we're going to do something at it so call some function process for every item in the list. And then update P to point to the next item, and keep going. And at the end of the list, the usual convention is that the pointer is the pointer to the next item from the last item in the list is a null pointer, so that will terminate the loop. So suppose that this process function is computationally expensive, and and doing it for every item in the list is independent. So we'd like to be able to execute this in parallel. So we can't directly use an OpenMP loop directive here, work sharing loop directive here. So potentially you can handle this without tasks, but what you would probably need to do is traverse the list and count how many items there are in it. That might not be that might be stored somewhere in the program, or it might not. You would then allocate an array of pointers of that size. You then traverse the list again and make a copy of a pointer to every item into the slot in the array, and then you could execute a regular for loop, which just traversed the array of pointers and called process. Okay, so it is potentially possible to handle this pattern without tasks, but it's rather ugly. It involves rewriting code. It involves extra memory to store the copies of the pointers, and it involves 2 sequential traverses of the list before you get to do anything in parallel. So it's possible, but it's not a particularly nice solution. However, tasks makes this pattern programmable in a really nice way. So again, what I'm going to do is use this parallel master pattern idea. Okay, so create a parallel region, then the master thread is the one that's going to traverse the list, and then every time for every item in the list, the process function is going to be wrapped up in a task. Okay. So that's very straightforward. The difficult thing, or the conceptually slightly tricky thing here, is what happens to P. Okay, and that's what this first private clause here is doing. Okay, so you are already familiar with first private from regular OpenMP loops. It doesn't get used that much. So for regular parallel regions and loops, you don't often need first private. So just to remind you what that does. Okay, so for a parallel region, first private gives every thread a private copy of the variable, and it gets initialized with the value that that existing variable had when the parallel region started. So this idea gets extended to tasks. So what the first private does here is it makes a copy of P for every task. Okay, so this is the idea again of having private data per task rather than per thread. And that private copy is initialized with the value of P when the task was generated. And then when that's stored alongside the task, so when the task actually get executed, then it will use that stored copy of P, stored private copy of P when the task actually gets executed. So that's what's going on here. Okay, so this first private makes a copy of P at the point where the task was generated. Okay, because the problem is that the master thread is immediately, as soon as the task is generated, the master thread is going to change, is going to get a different value of P. Okay, so we have to make sure, have some mechanism for storing the appropriate values of P alongside all the tasks. So that's what first private is doing here. Okay, and the Fortran version. Okay, so what's really going on under the hood here is useful to think about, because this pattern looks a bit weird at first sight. Okay, so what's really happening here is that thread 0, the master thread, is the one that's traversing the list. Okay, so it does the list traversal, but it doesn't execute any of those tasks, probably. Okay, all it's doing is packaging up the tasks. And then meanwhile, other threads are available to execute. Okay, so while there's some tasks available to do, other threads can be executing the tasks. And then most likely what will happen is that thread 0 will finish generating the tasks before they're all complete. Okay, so it's then free to join in and execute tasks as well. In fact, the runtime has even more freedom than this, okay, because it has to protect itself against generating having too many outstanding tasks and possibly using too much memory to store outstanding tasks. So it's actually possible that thread 0 does this for a while, okay. It then goes and executes some tasks, and then when the number of outstanding tasks is reduced by a bit, the master thread can go back into the back in at this point and carry on generating tasks. So really, the runtime has an awful lot of freedom to do stuff in whatever order it likes. Okay. So there are points in the code, so particularly when the beginning and end of tasks, they're called task switching points. Okay, so there are points where if the thread is allowed to stop doing what it's doing and go and do something else. Okay, So if you think of this as, again, so this piece of code is actually the implicit task. This is the piece of code which the master thread executes inside the parallel region. Excuse me. So that itself counts as a task. So there are certain points inside a task where a thread is allowed to stop what it's doing, go away and do something else, execute a different task, and then come back and resume what it was doing again. So yeah, there's really a lot of freedom for the runtime to organize the order in which computations happen, and we have pretty much no idea what it's going to do. Okay, and very little control over it. Okay. But eventually, the threads will all once all the threads have completed, they will all at some point arrive at the barrier, the implicit barrier at the end of the parallel region, and the parallel region will not complete until all the tasks have finished. Okay, any questions on any of that? So Raymond asks, is each task assigned to a separate thread? And if so, what happens when the number of lugs is greater than the number of threads? So tasks will be assigned to threads as threads become available. So if there are more tasks than threads, they will get executed by some thread at some point. Okay. So there's no direct linkage between tasks and threads. So what we're essentially doing is the parallel region creates a fixed number of threads, however many we ask for, and then we can generate as many tasks as we like. Tasks will get assigned to threads in some order by the runtime. So all the tasks will get executed by some thread at some point. Okay, and Chen is asking, can I control how many tasks to generate? Yes, but only explicitly. Okay, and I'll come back and talk about this a bit later on. Okay, because it's important that we don't try and generate too many short-running tasks. Yeah, I'll come back and talk about this later on, and how we might control it. Okay, so just to extend this idea a bit, okay, so far we've seen this pattern where one thread generates the tasks. Okay, we are not restricted to that. It's perfectly possible for multiple threads to execute task generation. So let's just extend this idea a little bit. So suppose instead of one linked list, we've got an array of linked lists, and we want to traverse them all and do the same thing for all of the lists. Okay, so we've got a loop over the lists. Okay, and we have an array of pointers to the heads of all the lists. We can handle it like that. Okay, so what we could do in this instance would be, it would be okay to execute this loop sequentially on the master thread, for example. So we could use the same pattern, but it might be a little bit more efficient to split up the task generation across threads as well. So we could simply use a work sharing for directive on this loop, on the loop over lists. So that means different threads are going to, so all the threads are going to participate in the task generation. So different threads are going to traverse different lists and generate tasks. Okay. So this is potentially quite a powerful idea, because we might have very irregular, tasks often help for cases where we've got very irregular parallelism. And in some sense, we've got nested parallelism here, okay, because we've got two levels. We've got a level of parallelism over the lists, so processing every list is independent, and then we've got parallelism inside the list. Processing every item in each list is also independent. So dealing with that kind of nested and irregular parallelism. So, we might be an example where everything is, we have no idea about load balancing here. So the lists could be very different lengths. The time that process takes to execute on different items could be very different. But what this kind of pattern does is that it allows the full freedom for the runtime to try and load balance everything. We're just going to generate all those tasks, and then however long they all take, then the runtime has the opportunity to spread those tasks dynamically across all the threads and try and achieve load balance. So tasks are useful for this kind of irregular nested parallelism, where conventional methods might find it very difficult to load balance everything. And I'll come back to this actually when we talk about nested parallelism later on, okay? Because we actually have this. Sometimes we can have this choice. Do we do nested parallel regions? Do we do nested tasks, or some combination of the two? We have they're both mechanisms for dealing with nested parallelism. What's the difference, and what are the strengths and weaknesses? And we'll come back and talk about that later on in the nested parallelism session. Okay. Data scoping. Okay, so actually a lot of the difficulty of programming with tasks is getting the data scoping right. Okay, so whether variables should be shared private or first private with respect to tasks. So reasoning about that and getting that right is a little bit tricky. So these concepts are a little bit different compared with threads. Well, yes and no. Okay, if you think about nested parallel regions, then actually the ideas are really quite similar. Okay, or at least the same ideas also apply to nested parallel regions as well as to tasks. Okay. But the way to think about it is like this. Okay, if a variable is shared on a task construct, then the references to it inside the construct are to whatever storage there was with that name at the point where the task was encountered. Okay, so if it's shared, it means just use the existing storage and don't make any new copies. The slight complexity here is that existing storage could be private to the thread. Okay, so it's perfectly possible to have a variable that's private to the thread that's generating tasks, but is shared between all the tasks that thread generates. So this is the kind of added bit of complexity that we need to get our heads around with data scoping. Because the data scoping with respect to the tasks can be different to the data scoping with respect to the threads in the parallel region that are generating them. Okay, private is quite straightforward. Okay, private on a task means that the reference to it inside the construct that's new uninitialized storage that gets created when the task is executed. Okay, so that's a new private copy. It just exists for the duration of the task and then disappears afterwards. Okay. And then the third possibility is first private, which we've already seen the example of that with the linked list example. So in this case, that's going to be first private on a task construct, references it to our new storage that gets created and initialized with the value of the existing storage of that name when the task is encountered. Okay. So the copy is made when the task is generated and the existing value is copied into it. Okay, so as with parallel regions, there are default rules, which I'm going to talk about, and then I'm going to encourage you not to rely on them. Okay, so, and they're different from what you would normally expect. Okay, so the behavior that you want for tasks is usually first private. Okay, so unless you have unless data is essentially read only, and you just want all the tasks to read the same thing, most of the time you want first private copies, so that every task has its own copy of things. Okay, so the rule is that variables that are private when the task private to the thread when the task construct is encountered are made first private for the task by default. Okay. And only variables that are shared in all constructs starting from the innermost enclosing parallel constructs and going outwards are shared by default. Okay. So the default rules are rather messy and confusing. So for example, in this example, suppose I have a parallel region. At the parallel region level, I have a variable A, which is shared, and a variable B, which is private. And then I have a task which doesn't specify anything, any shared or private or first private clauses on the task. Then the default rules say that inside the task, A will be shared, but B will be made for you'll get a first private copy by default, because it's private to the thread. Okay, there. Right. And then if I want a private copy, well, I would probably just I could either do one of two things in C or C++. The natural thing would just be to declare something inside the task. So that would be a private copy that existed only for the scope of the task. In Fortran, you might say, okay, you can't do the declarations inside tasks, so you'd a private clause explicitly to make a private copy of C for every task. Okay, any questions about that? So as I say, I'll remind you in a minute. Okay, I always for all OpenMP, I strongly encourage the use of default none. Okay, I think this is probably the fact that the default behavior is essentially default shared for parallel regions, and it's something messy, and the default behavior is something messy and complicated for tasks. I strongly recommend that you don't rely on the default behavior for data scoping. So I strongly recommend the use of default none, so both for parallel regions and for tasks as well. So you can put a default none clause on a task, and then that forces you to explicitly declare everything that's accessed inside the task as shared, private, or first private. Okay. Any questions about that? Okay. So another potential interesting use case for tasks is recursion. So sort of parallelism that you get from divide and conquer algorithms, which are sort of naturally recursive, where you basically you have a problem, you split it into multiple parts, usually two, and then apply the same algorithm recursively to split things down until you've got enough parts to execute in parallel, and then you potentially join all the bits back together again to form a solution. Okay, so I don't know about you, but I find thinking about recursive programs hard. I usually understand them for about 5 minutes, and then I have to think again. So this is every computer scientist's favorite recursive program to compute Fibonacci numbers. But I should just note that I'm absolutely completely aware that this is a stupid, inefficient way of computing Fibonacci numbers, but it serves its purpose for this, for an example. Okay, so Fibonacci numbers. So the nth Fibonacci number is the sum of the previous two. I'm sure you all know about that. So one way of computing this, say stupidly but recursively, is to have a recursive function fib. Okay. Which takes the value n, and then once we get down to 1, we just return 1. Otherwise, we call fib recursively for n-1 and n-2, and then add the results together and return that. And then, for example, we have to kick off the recursion somehow. So if we want to know the 5,000th Fibonacci number, we start off the recursion at the top level. Okay, so again, this is not easy. This sort of recursion is not easily handleable by other mechanisms in OpenMP. But it is nicely handleable with tasks. Okay. So what we can do is, and this is going to be, because it's recursive, this is going to be nested tasks. So again, this gets even harder to reason about. So think carefully what's going on here. Okay, so what we can do is put each of these recursive calls inside a task construct. So every time every time this happens, then we create a recursive call, and we basically kick off a task for each of these recursive calls, but then we have to wait for them to finish. Okay, so we use a task wait to do that. Okay, so again, you have to think carefully about this. So task wait is only waiting for the immediate children, but there's a task wait at every level of the recursion. So in fact, you are by implication waiting for all descendants here. Okay, but it's not doing it directly, it's doing it implicitly because there's a task wait at every level. So once once these two recursive tasks have completed, then we can add the results together and recurse back up. Okay. So the tricky thing here again is the data scoping. Okay. So, and this looks weird, and you need to think carefully about it. Okay. So what happens? What do we need for these values x and y here? What should their scope be? Okay. And the answer, perhaps a bit surprisingly, is that they need to be shared. Okay. Why? Okay. It's because that these references to x and y really need to be references to the existing storage. Okay, the existing storage is these copies of these local variables, which are created at every level of recursion. So X and Y really have to refer to these two variables declared here. And also, X and Y cannot be private because they would go out of scope as soon as the task had completed. So when we reference them here, they wouldn't exist anymore. So again, you have to think about, so what does shared mean here? Shared means use the existing storage of that name. Okay, so it says, so that means that X and Y here really are this existing storage, which was created by the parent task, which called this function recursively. So that's a little bit hairy to think about. Okay, so of course we need to create some threads and kick off the recursion, so we can just use the usual parallel master pattern to close the original call at the top of the recursion tree. So that's quite a powerful use of tasks, but as I say, it's not particularly easy to reason about. It's a little bit tricky. So it'll run. Will I run out of memory? Potentially, yes. Okay. Though again, the runtime has freedom here. It can stop generating tasks and go away and execute them. So it can, threads can. It's also possible that that an encountering thread can immediately execute the task itself and not package it up. So the runtime has quite a lot of freedom to do things that will defend against running out of memory. Okay, and Fortran version. Okay, so some hints about using tasks. So as I've kind of said already, getting the data attribute scoping can be quite tricky. The default rules are different, and using default none is a really good idea. Okay. In general, you probably shouldn't use tasks for other things which are already well supported by other OpenMP features. So, for example, for the regular sort of do or for loops, tasks will work, but the overhead of using tasks is greater. Okay, so the need for more complex internal data structures to store the tasks, store the outstanding tasks, and associated first private data costs something, and that's that causes some overhead. And yeah, okay, so the runtime implementations of tasks are generally reasonably good, but you can't expect miracles. Okay, if you try and generate gazillions of tiny short-running tasks, then you will just drown in the overheads. So you may need to think a little bit carefully about the granularity of the tasks that you generate. And that might mean that the natural tasks that occur in your code or in your algorithm are not big enough to create as real OpenMP tasks. You might need to group the natural tasks the natural computational tasks together into a single OpenMP task in order to get tasks which are big enough. There's always going to be some tension here. Okay, if I have too many tiny tasks, I'm going to run into the overheads of storing them and scheduling them and so on. If I have too few large tasks, then it might be difficult to keep all my threads busy, and I might not get a good load balance. So, you know, it's often when you're programming with tasks, you're thinking about, can I find that optimum, or it might be a range of optimum sizes. It might not be too sensitive. So it might be that you need to think about, you know, having some control over programming in some control over the granularity. Okay, to have some parameter in the code where you can, which allows you to control the sizes of the OpenMP tasks that are generated. Okay, so for example, let's go back to our list, our linked list chasing algorithm again. So you might think, well, actually, maybe, you know, maybe we need to refactor this so that rather than so instead of processing one item at a time, we refactor the code so that process actually processes n items at a time. Okay, so we make this, you know, make this call. So we make the body of the task more computationally expensive. Okay, and then you basically skip over, you know, to get to the next task, you skip over the next n items, and the process internally traverses the part of the list. So, you know, now this would give you, you know, if n items is a parameter that you can choose, then that gives you a way of controlling the granularity. Okay, so, you know, different use cases of your code, depending on what it's doing, might require, you know, depending on, you know, how many threads you're using, you know, how expensive this function is for a particular use case, then you might, and this at least gives you a tunable parameter that allows you to control the granularity of the tasks. Okay. Again, for the Fibonacci case, you can think of doing something similar. Okay. The task construct has an if clause available on it. And what that does is that if the if clause evaluates to true, then we'll create a task. If the if clause evaluates to false, then we don't create a task, but the encountering thread just executes the block of code straight away. So what you could do for the Fibonacci case, again, so, you know, you might end up, if you go right down, I mean, the Fibonacci case is stupid, right? The amount, the computation down at the bottom of the tree is essentially zero. Okay, so generating, it just generates, you know, this particular example just generates gazillions of tiny tasks, and you'll just drown in the overheads. Okay, so you probably want to stop recursing at some level. Okay, or at least you stop generating tasks at some level and just do sequential recursion below that. So you can use the if clause to do that. Okay, so again, you know, you could maybe have a parameter here that allows you to choose the level at which you stop generating tasks and just do sequential recursion. Okay, any questions about that? Okay, a couple of other things to mention about tasks. Okay, so sometimes you might want to just have, you know, you have a loop where you basically want to turn the body of the loop into a task. Okay, and you can do that by just rewriting it, but it's again, you might want some control over how many loop iterations go into a separate task, and there's this convenience mechanism called task loop, okay, which basically does it for you. Okay, so if you have a regular loop, the sort of loop where you can do work sharing on, instead of doing the usual work sharing thing, you can use task loop. Okay, and then you can choose the grain size. Okay, so this is equivalent to chunk size parameter for schedule clauses. So you can choose. So this says every 16 iterations of the loop forms a task. Okay. So you can either do it that way, or you can also specify, alternatively, you can specify how many tasks you want to generate, and then it'll compute the grain size for you, depending on, from the value of n and the number of tasks you want to generate. So it just gives you a bit of convenience to saving you having to refactor code to do that. So I mentioned before that task weight and task group are one way of enforcing some ordering between tasks, but that's only suitable for certain simple patterns. You can also have explicit dependencies between tasks. Okay, so this is done with the depend clause, and this basically works on addresses. Okay. So we're basically specifying that that tasks either have an in dependency or an out dependency on a certain address or list of addresses. Okay. So basically, what it says is that if it's an independency, then this task will be a dependent task of all previously generated sibling tasks. Okay, so sibling means generated at the same level of nesting. Okay, so we can only have, with this mechanism, we can only have dependencies between tasks at the same level of nesting. Okay, so all previously generated sibling tasks that reference at least one of the list items as an out dependency. Okay, and out, or so actually in out is both in and out, but actually the way things are specified, out and in out are actually synonymous semantically. But it might be, if you really have an in and out dependency on a certain item, then it might be clearer to programming it as to write it as an in out dependency. But the semantics are just the same as out. Okay, so in that sense, the generated task will be a dependent task of all previously generated sibling tasks that reference at least one of the list items, either as an in or an out, or an in-out clause. Okay, that's a bit of a mouthful. It's a bit hard. So simple example, for example, would be something like this. Okay, and suppose I have 3 tasks, and that I'm in a situation where the first 2 tasks can execute in parallel, but the third one can't start until both the first 2 are complete. Okay, so I could specify the first task, I could give it an out dependency on some variable A. Second task, give it an out dependency on B, and the third task, give it an independency on both A and B. So that means that although all these, if a thread executes this code, it'll generate all the tasks. So it keeps, it doesn't, the encountering thread here doesn't block. Okay, it generates all the tasks, but it just means that when the tasks come to be executed, then this task cannot start executing until both these tasks, which it depends on, have completed. So because you can have array elements and array sections and any old variables and more complicated data structures inside these dependency clauses, it's possible to build quite complicated, possible to specify and build quite complicated dynamic task graphs with this kind of mechanism. Okay, and the final thing I want to say about tasks is that there's a complication with reductions. Okay, unfortunately, it's not. We can't simply use reduction variables inside tasks as you might hope. Okay, so for example, if I had a parallel region with a reduction variable A at the parallel region level, then I'm not allowed to access that variable inside tasks. Okay, that's not supported. The reason is that it's quite it's just an implementation difficulty. It's quite hard for the implementation to track what this is supposed to refer to if it's a reduction variable. Yeah, okay. So one way to get around that is just to not reuse reductions. Okay, is to say just make A shared and then do atomic updates to it. Okay, that's possible, at least for basic types, but it might be a bit inefficient. Okay, you have lots, might end up with lots of atomic updates to something which you would avoid with which you're trying to avoid by using reduction anyway. If you do want to use reduction variables, there is a way of doing it with task group. Okay, so all the tasks that access the reduction variable have to be inside a task group. We declare it as a task. Instead of reduction, we have a task reduction clause on the task group. Okay, and then we also have to specify on the task. We also have to tell the runtime that this task is going to access this reduction variable. So it's a little bit messy. Okay. And in this case, the reduction in operations are actually going to happen at the end of the task group. So it is possible to do reductions with tasks, but it's a little bit more complicated and messy than you might like. Okay, that's the end of this one. Anybody have any final questions? Okay, thank you. So what I suggest we do is we give ourselves a 5-minute break, and I'll start the next session at 25 past. Okay, so our second topic for today is nested parallelism. So yes, nested parallelism is supported in OpenMP. So what happens if we encounter a parallel construct inside another parallel construct, then a new team of threads will be created for that inner parallel construct. Usually this needs to be enabled, okay? So we have control over this either through the OMP nested environment variable, you need to set that to true, or by calling the OMP set nested routine from inside the code. So the way this works is that if nested parallelism is disabled, the code will still execute, but the inner teams will contain only one thread. Okay, so they won't. Inner teams will just execute on the encountering thread, and no new threads will be created at the inner level. Okay. Okay, this is for our Fortran programmer. This is a Fortran example, but we all get the gist of it. Okay. Suppose we have we get a pointer here. Okay. Suppose I have two loops. Okay, which are in principle parallel. Oh, my formatting's got a bit messed up there. So we want to share those loops out between threads, but we also want to execute the two separate loops in parallel as well. Okay, so for example, what we could do is create a parallel region at the outer level, which we're going to arrange, and I'll talk about how we arrange thread numbers in more detail in a minute. But suppose we create an outer region with two threads. And then thread 0 is going to encounter a parallel do. So that's another parallel region. So it will create some threads. So I would say 4 threads to share out the iterations of this loop. Otherwise, thread 1 at the top level is going to create a different team of 4 threads to execute this loop. So we can do that. Okay. There's the equivalent example for C programmers. Okay. So it turns out this is, it's an interesting feature, but it's not actually used that much in practice, I don't think. It can be useful if the outer level, if you have an algorithm which has multiple levels of parallelism, but the outer level doesn't have enough parallelism to keep all our threads busy. So it might be instances where there's a fixed amount of parallelism at the outer level. If you can't divide up any more, or we want to use, might be a situation where we want to use a lot of threads, and we can't get enough parallelism at the outermost level. Okay. There is some implementation extra implementation required to enable it. So implementing it correctly without impacting performance a bit is actually difficult. So that's why it's usually disabled by default. Okay, so the default behavior depends on which compiler you're using, but most of them turn off nested parallelism by default. And you shouldn't enable it unless you're actually using it, because it does actually cause some additional overheads. Okay, the possible existence of multiple teams executing concurrently requires a bunch more bookkeeping and potentially synchronization inside the runtime that you don't need if you just have one level of parallelism. Okay, so how can we control the number of threads? So we can actually do it with the environment variable. Okay, so OMP numthreads environment variable will accept a comma-separated list of values, which tells the runtime how many threads to use at each level of parallelism, starting from the outermost one. Okay, so if I set OMP numthreads to 2, 4, then that we use 2 threads at the outer level and 4 threads for each of the inner teams. So that's one way of doing it, quite convenient, provided we want every inner team to have the same number of threads. Okay. There's other ways of doing it as well. We can use OMP set numthreads function, or there's a numthreads clause on the parallel region. So we'll take a look at both of those. They are sort of equivalent, but there are sort of choices about what you want to do, which are maybe more down to software engineering concerns. Okay. So potentially if you want your inner regions to use different numbers of threads, then you could do that. Okay, so suppose I have, okay, so let's just focus on the actual code here. So I've got an outer loop here, outer I loop with 4 iterations, and then each of those I iterations contains a J loop with, say, lots of iterations, with n iterations in it. Okay. So what the way this actually works in OpenMP is that OpenMP has these entities called internal control variables. So these are essentially variables which are not directly accessible inside the runtime. And one of these variables is called nthreadsvar, and every thread has its own copy of nthreadsvar. And what nthreadsvar does is that controls the number of threads that would be created if this thread comes across a new parallel construct. Okay, so and OMP set num threads is setting the value of that internal control variable. So if I call OMP set num threads to be 2 here, so this is on the master thread outside any parallel region, then that means that it will use 2 threads for the outer parallel region. And then when I'm inside that region, I can call OMP set num threads again, and suppose I have some thread numbers, I can choose whatever I like, maybe and store them in an array somewhere. So I can potentially use a different number of threads for every single instance of this inner parallel region inside this I loop. Okay, so I think what's going to happen here at the outer level, I've got 2 threads. So thread 0 is going to execute I equals 0 and then I equals 1. Thread 1 at the outer level is going to execute I equals 2, then I equals 3. So there's going to be 4 separate instances of this inner parallel region, and I could potentially choose a different number of threads for all of those 4 different instances. And I can do that by calling set OMP set num threads, because this call only affects the number of threads that will be generated by the calling thread. So every thread can have a different value of this internal control variable. So unfortunately, internal control variables were not introduced at the very beginning of OpenMP. So it means that the runtime library routines don't have the right, or don't have the appropriate getter and setter names. Okay, so OMP set num threads is the setter function for the internal control variable, but OMP get num threads is not the getter. Okay, OMP get num threads returns the number of threads executing inside the current parallel region. There is a getter method for a getter function for the internal control variable. It's called OMP get max threads. So you can inquire that the current value of that internal control variable. It's just that the function doesn't quite have the name that you might expect. Yeah, and so anything you do with that overrides, and so the environment variable gives an initial value to those internal control variables, but this function will reset it and override it. The other way of doing it is using a num threads clause. So you can put a num threads clause on the, my coloring's gone wrong here as well. You can put a num threads clause on the parallel region. And that does the same thing, but it doesn't change it just overrides the internal control variable and doesn't modify it. So you can choose to do it either way. Again, this is really a software engineering issue. So, do you want the number of threads to be specified, at the point where you're creating the parallel region? Okay. In that case, you might want to, if you've got lots of parallel regions in your code, you might have to, you might end up having to edit a lot of, to add this to every single instance of parallel region. That might not be very convenient. On the other hand, if you use OMP set num threads, you have to be a little bit careful because this call can happen anywhere in the code. Okay, so burying calls to OMP set num threads somewhere deeply nested inside inside the call tree somewhere is a bit nasty. Okay, because it's it can be not obvious where that's being set. Okay, if you do it like this immediately before the parallel region, well, that's fine. But if you want to do it once somewhere, then you have to be careful. That, and also you probably also need to be careful about hard code. This is bad. Okay, bad practice to hard code thread numbers like this because it overrides OMP num threads. I've seen cases where somebody's done that, not necessarily for nested parallelism, but just for just to set the number of threads. I've seen cases where there's a hard-coded OMP set num threads called somewhere, right? Somewhere buried inside a large piece, a large number of code files, and then you wonder why. Setting the environment variable doesn't seem to do anything, and you have to go, and find that hard-coded thing. So, yeah, it's really down to software engineering issues as to which of these mechanisms you might want to use. Okay, there's more control you can have. Okay, it's very easy with nested parallelism to end up generating lots of threads, and as usual, you probably don't want to generate more threads than you have the appropriate hardware resources. So whether that's hardware threads or physical cores, you probably want to limit. It's useful to be able to limit the total number of threads that are going to be generated and match that to the hardware resources you have access to. So you can do that. There's an environment variable, OMP thread limit. So you can set that, and that basically puts an upper limit on the number of threads that will be running at any one time. So if that gets exceeded, then any parallel region will not that subsequently gets encountered won't create any more threads. Though at some point, obviously, at some point in the future, that some parallel regions may finish, so the total number of threads reduces, and then new parallel regions can create more threads. Can also control the maximum depth of nesting. Okay, so this is actually now the approved way to enable nested parallelism. Is not to use OMP nested environment variable. It's to set OMP max active levels to something greater than 1. So this can be useful in cases there can be instances where you have say a library, a multi-threaded library which has OpenMP inside it, and then you might be calling that from your application code, which itself has OpenMP in it. So you might want to use it to control whether depending on whether your library calls are coming from inside parallel regions or outside parallel regions, you can use this kind of mechanism to control whether you're actually using nested parallelism or not. Okay. So there's other routines that allow you to navigate. So you end up, creating basically a tree of threads with nested parallelism. So there are utility routines for navigating around the tree. So OMP get level gives you the level of parallelism. Okay, so in the sequential part of the programs are outside any parallel regions, that will return 0, and then 1 inside the first level of nesting, and so on. Get active level does the same thing, but it ignores levels which are inactive. Okay, so in an inactive level of parallelism is a team that only contains one thread. Okay, so get active level tells you how many levels of parallelism you are that actually created threads. And then for a given level, you can get your ancestor thread number, so you can figure out the level of the number of your thread at different levels in the tree above you. Okay, so for example, if you want the ID of your parent, you would call get level, subtract 1 from it, and then pass that to ancestor thread number. And you can also get team sizes at levels above you as well. Okay, of course, there's no way of getting team, there's no way of inquiring about team sizes of sibling regions or other regions that might be active. You can only go upwards. Okay. So just to mention that there is, there's one particular use case where you might think about using parallel regions, but there's actually a better way of doing that, and that's if we have perfect loop nests and you want to parallelize more than one loop in the nest. Okay. So provided we have perfectly nested rectangular loops, then we can use the collapse clause instead. Okay, so a situation like this, so we have in this case, a doubly nested loop. So what do these terms mean? Perfectly nested means that all the executable statements are inside the innermost loop. Okay, so there's no code between the loops, between the starts of the loops or between the ends of the loops. And rectangular means that the bounds of the inner loops don't depend on the iterators of the outer loops. So for example, if instead of j less than n here, suppose I had j less than I, then that would not be a rectangular loop. But provided we're perfectly nested in rectangular, then we can parallelize both loops across a team of threads by using the collapse clause. So the argument to the collapse clause is the number of loops you want to parallelize, counting in from the outside. Okay. Because you might have other loops inside here which you don't want to parallelize, for example. Okay, so you might have a nest of 4 loops, but you only want to do the outer 2. So what this will do is that the compiler will transform this into a single loop, a single long loop of length n times m iterations, and then it'll parallelize that and apply any schedule clause to that generated long loop. Okay, so the chunk, if you put a chunk size in the schedule, then the number of iterations in a chunk it's talking about the iterations of the generated long loop. So this is useful in the case, so for example, if the value of n here is approximately the number of threads, okay? So if it's exactly equal to the number of threads, then you might be fine, okay? But if it's slightly less than the number of threads or slightly more than the number of threads, then you're not going to get very good load balance by just parallelizing the outermost loop. Okay, So if you're in that kind of situation, then it might be useful to exploit parallelism in more than one loop in the nest. And for this particular use case, this is going to be typically more efficient than using nested teams. Okay, so you could do with this with nested parallelism, use a parallel for on both loops, and then figure out how many threads you want at each level and so on. But the collapse mechanism is going to be more efficient, generally speaking. Okay. I have to think about synchronization in nested parallelism a little bit. Okay, so barriers, whether either explicit or implicit barriers, only affect the innermost enclosing parallel region. Okay, so there is no way to have a barrier that operates across multiple teams. On the other hand, things like critical regions, atomics, and locks affect all the threads in the program. Okay. So if you want, mutual exclusion within teams but not between them, then you might want to use a lock. You might need to use locks rather than critical regions. You might use to create a lock per team and use that. Or atomics might work, provided they, if different teams are accessing different data items, then atomics should work fine. Okay, so I mentioned earlier that we can have this choice. If we have nested parallelism in our code or in the underlying algorithm, then for OpenMP implementation, we have this potential to have this choice of whether to use nested teams or nested tasks. And the answer is, well, it depends. Okay, if we have very regular parallelism, so like regular loops over multidimensional arrays, very regular data structures, everything's going to be nicely load balanced, then nested parallelism can be good because that gives us more control over thread affinity and data affinity. So with nested parallelism, it allows us to bind threads to cores. And for example, if you make sure that we can make sure, if we want to, that threads within a team are on neighboring cores so that they share some last level cache, for example. And we can also make sure that that a given team is always accessing the same set of program data, so we get good data affinity. On the other hand, if we use tasks, then we've basically got no control over which thread tasks will execute on, and therefore tasks might execute on any core, and that might not result in the also optimal caching behavior. On the other hand, if we've got very regular problems, it's really hard to achieve load balancing with nested teams. I mean, you can have different sized inner teams, as we've seen, but that's not that's a rather crude and not a dynamic solution. And it can be difficult to estimate. You have to think about how much work does how much work is there in each of the different teams, and try to choose a right number of threads. It's possible, but it's generally very unsatisfactory way of trying to load balance by creating teams of different sizes. On the other hand, we see with nested tasks, then any thread can execute tasks from any level of nested parallelism, and it's really just we can just specify the tasks and let the runtime get on with the job of doing all the load balancing for us. So yeah, it's a choice. You know, it depends on the situation and the type of and the type of problem we're trying to solve as to whether it's, you know, whether you'd want to use nested teams or nested tasks. Okay. So Chen asks, nested parallel regions are actually multiple nested parallel regions or merged into one? I'm not quite sure what you're asking here. No, they really are nested parallel regions. They're not merged. Okay, you nested parallel regions. You really do create new threads. So I mean, implementations generally try to reuse the underlying kernel threads. So what implementations typically do is they look at the value of the environment variable of OMP num threads that you set, and they will initially create that number of threads. Usually it usually happens at program startup actually, rather than when you get to the first parallel region. But that does depend on the implementation. And so the implementation will maintain a pool of kernel threads. And if you ask for more, then it'll go and create more. But it will try and reuse them rather than just continually creating new ones. Okay? So the implementation will typically maintain a pool of the underlying kernel threads to implement the OpenMP threads and reuse them where it can, but it will just go and create additional ones if it needs to. Okay, in that case, that's it for today. Please feel free to have a go at the practical exercises. So there's basically a simple piece of code where you can play with both. You can try nested parallelism and tasks and get some feeling for how that works. So please feel free to do that if you'd like to. And if you've got any questions or about them, then please feel free to drop me an email. So I'll just post my email's in the introductory slides, but I'll just post it here anyways as well. Okay, thanks very much, everybody, and I'll speak to you again on Thursday.